Welcome, everyone. I'm excited to kick off today's presentation on surface chemistry. This is the first slide, and it sets the stage for what's to come. We'll be exploring the fundamental aspects of surface chemistry and its applications. From the basic principles to real-world examples, there's a lot to cover. But for now, let's get started and dive into this fascinating topic. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's start with the basics. When we talk about bulk phases, we're referring to the large, continuous regions of matter, and in this case, we're focusing on liquids. The term liquid-liquid highlights that both phases involved are liquids. These interfaces between liquids are fascinating because they exhibit unique behaviors and properties that differ from the bulk phases themselves. Understanding these interfaces is crucial in many fields, from industrial processes to biological systems. For example, in emulsions, the interface between oil and water, both liquids, determines stability and functionality. This brings us to the core idea of surface chemistry. It's all about the processes that happen right at these interfaces. So, in essence, surface chemistry helps us understand how molecules interact at the boundary between two phases, influencing phenomena like adhesion, wetting, and even chemical reactions. Recognizing these interactions is key to controlling and optimizing many practical applications. This slide sets the stage for exploring the specific behaviors that occur at liquid-liquid interfaces and how they impact the broader science and technology we're discussing today. Let's start by looking at adsorption. Adsorption is essentially the process where atoms, ions, or molecules, whether they're from a gas, liquid, or dissolved solids, adhere to a surface. Think of it as these particles sticking to a surface without becoming part of the bulk material. It's a surface phenomenon, and it plays a crucial role in many processes, from filtration to catalysis. Now, contrasting that with absorption. Absorption involves these same particles, atoms, molecules, or ions, entering into the bulk phase of a material, so they're not just sticking to the surface, but actually penetrating into the interior. This can happen physically, like when a sponge soaks up water, or chemically, when a substance reacts and becomes part of the material. When we talk about the types, it's important to understand that adsorption and absorption are distinct, but sometimes interconnected processes. Each has its own mechanisms and implications, especially in fields like environmental science, chemistry, and material engineering. Recognizing the difference helps us better understand how materials interact with their surroundings and how we can manipulate these processes for various applications. Today, I want to talk about adsorption on activated charcoal, which is a really important process in many filtration and purification systems. Essentially, adsorption is when molecules from a liquid or gas adhere to the surface of a solid, in this case, activated charcoal. Activated charcoal is highly porous, giving it a vast surface area, which makes it incredibly effective at trapping impurities. When a contaminated fluid passes through or over the charcoal, harmful substances like toxins, chemicals, or odors are attracted and stick to the surface. This process is crucial because it helps purify water, air, and even certain chemicals in industrial applications. The key point here is that adsorption is a surface phenomenon. The more porous and extensive the surface, the more contaminants it can capture. Connecting this to the overall theme, understanding how activated charcoal works helps us appreciate its role in health, safety, and environmental protection. It's a simple yet powerful method to remove unwanted substances efficiently. Today, I want to talk about absorption through a membrane, which is a fundamental process in many biological systems. Essentially, absorption involves the movement of substances, like nutrients or chemicals, across a membrane. This membrane acts as a selective barrier, meaning it allows certain molecules to pass through while blocking others. The key point here is that this process isn't just about simple diffusion. It often involves specific mechanisms that help substances cross membranes more efficiently. For example, there are active transport processes that require energy and passive processes that rely on concentration gradients. Understanding how absorption works is crucial because it underpins many functions, from nutrient uptake in the digestive system to drug delivery in medicine. By studying these mechanisms, we can better comprehend how organisms interact with their environment and how we can improve therapeutic interventions. In the context of the overall presentation, remember that membrane absorption is a central theme. It connects the physical properties of membranes with their biological functions and their importance in health and disease. Let's take a closer look at what's happening during these two phases. In phase I, we have adsorption, which is essentially the process where the adsorbate, meaning the substance that is being collected, attaches itself onto the surface of the adsorbent. Think of it as a kind of surface sticking. This is a critical step because it determines how effectively the contaminant or target molecule is captured. Then, moving into phase II, we see absorption, which is sometimes called partitioning. Here, instead of just sticking on the surface, the adsorbate actually penetrates into the interior of the adsorbent material. It's more like being absorbed into the substance, spreading throughout it. Understanding these two phases helps us grasp how different materials work for purification or separation processes. The key point is that adsorption is about surface interaction, while absorption involves the entire volume of the adsorbent, which can influence how we select materials for specific applications. This whole process ties back to our overall goal of efficiently removing or isolating certain substances. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about adsorption. This is the process where molecular species, or substances, tend to gather at the surface of a solid or liquid, rather than being spread throughout the entire bulk. It's a surface phenomenon that plays a crucial role in many chemical and physical processes. The molecule or substance that gathers at the surface is called the adsorbate. Think of it as the substance that's sticking to the surface. On the other hand, the material that provides the surface for this accumulation is known as the adsorbent. Understanding this distinction is key because it helps us analyze how different materials interact at their interfaces, which is central to many applications, from catalysis to environmental cleanup. So, in essence, adsorption involves the surface accumulation of molecules, with the adsorbate being what gathers there, and the adsorbent being what hosts that gathering. This concept ties directly into the overall theme of surface interactions and their importance in science and technology. Let's begin by looking at how gases interact with charcoal. When gases like oxygen, hydrogen, carbon monoxide, chlorine, ammonia, or sulfur dioxide are placed in a closed vessel with powdered charcoal, you'll notice that the pressure inside the vessel decreases. This is because the gas molecules tend to gather at the surface of the charcoal, effectively being adsorbed there. So, adsorption involves the gas molecules sticking to the surface, reducing the amount of free gas in the space. Moving on to solutions, if you take a dye like methylene blue and add animal charcoal, then shake the mixture well, you'll see that the liquid becomes colorless. This shows that the dye molecules are being attracted and held on the surface of the charcoal. Again, adsorption. The dye molecules don't go into the charcoal but stay on its surface, removing color from the solution. Similarly, when raw sugar solution passes over beds of animal charcoal, the solution turns colorless. That's because the coloring substances in the sugar solution are being adsorbed by the charcoal, which traps them on its surface. And if you've ever seen silica gel in packaging, you've probably noticed it absorbs moisture from the air, making the environment dry. This is because water molecules are adsorbed onto the surface of the silica gel particles, removing humidity from the surroundings. Now, an important concept to remember is desorption. This is the process where an adsorbed substance is removed from the surface. So, when we want to recover substances that have been adsorbed, or when the adsorbent needs to be regenerated, desorption is the key process. Throughout all these examples, the core idea is that adsorption involves molecules sticking to a surface, and it's a vital process in many practical applications, from purification to drying. Now let's look at the key differences between adsorption and absorption. In adsorption, the substance, or the adsorbate, concentrates only on the surface of the adsorbent. It doesn't penetrate through the surface into the bulk of the material. Think of it like a sponge that only holds water on its surface, not throughout its entire volume. On the other hand, in absorption, the substance is uniformly distributed throughout the entire bulk of the solid. So, instead of just sticking to the surface, it penetrates into the material itself, filling the entire volume. To make this clearer, consider water vapor as an example. Water vapor gets absorbed by anhydrous calcium chloride, meaning it penetrates and spreads throughout the calcium chloride. But if you have silica gel, water vapor is just adsorbed onto its surface, not absorbed internally. In simple terms, in adsorption, the concentration of the adsorbate increases only at the surface, whereas in absorption, the concentration becomes uniform throughout the entire solid. It's also important to note that both processes can happen at the same time, which is why we use the term sorption to describe both. Understanding this distinction is crucial because it helps us interpret how different materials interact with substances, which ties back to the overall theme of material behavior and surface interactions in our presentation. Inside the adsorbent, all the forces acting between the particles are mutually balanced, meaning that within the bulk of the material, these forces are in equilibrium. However, on the surface, the situation is quite different. Surface particles are not surrounded on all sides by atoms or molecules of the same kind. This creates an imbalance of forces, leading to what we call residual or unbalanced attractive forces at the surface. These residual forces are crucial because they are responsible for attracting the adsorbate particles to the surface of the adsorbent. Think of it as the surface having a kind of pull or attraction that draws in other molecules from the surrounding environment. Now, the extent or amount of adsorption that occurs depends significantly on the surface area of the adsorbent. Specifically, the larger the surface area per unit mass, the more sites are available for adsorption. So, if you have a bigger surface, you can attract and hold more adsorbate molecules, assuming the temperature and pressure remain constant. This is a key idea because it connects the microscopic forces at play with the practical aspects of designing effective adsorbents. More surface area generally means better adsorption capacity. And this brings us to the overall mechanism of adsorption, which is essentially about the interaction between these unbalanced surface forces and the molecules in the surrounding environment. Another important factor in adsorption is the heat of adsorption. During this process, we always see a decrease in the residual forces on the surface, which means a reduction in surface energy that shows up as heat. So, essentially, adsorption is an exothermic process, meaning it releases heat. In fact, the change in enthalpy, H, for adsorption is always negative. When a gas gets adsorbed, its molecules have less freedom to move around. This restriction causes a decrease in entropy, so S is negative. In simple terms, both the enthalpy and entropy decrease during adsorption. Now, for a process to be spontaneous, thermodynamics tells us that the Gibbs free energy change, G, must be negative. At constant temperature and pressure, this is our key criterion, and we know that G is calculated as H minus T times S. Here's the interesting part. G can only be negative if the negative H is large enough to outweigh the positive TS term. So, in spontaneous adsorption, both the negative enthalpy and the decrease in entropy work together to make G negative. As the adsorption continues, the magnitude of H becomes less negative, approaching the point where H equals Ts, and then G reaches 0. That's the point where equilibrium is established, meaning the rates of adsorption and desorption are balanced. There are mainly two types of adsorption of gases on solids that we need to understand. The first one is called physical adsorption, or physisorption. This occurs when gas molecules accumulate on the surface of a solid due to weak van der Waals forces. These are relatively weak interactions, meaning the gas is held loosely to the surface. The second type is chemical adsorption, or chemisorption. Here, the gas molecules or atoms are held to the solid's surface through chemical bonds, which are much stronger. These bonds can be covalent or ionic in nature, involving a more significant transfer or sharing of electrons. Chemisorption typically involves a higher energy of activation, which is why it's sometimes referred to as activated adsorption. It requires more energy to initiate, but results in a stronger, more specific attachment to the surface. An interesting point to note is that these two processes can sometimes occur simultaneously, making it tricky to distinguish between them. For example, at low temperatures, physical adsorption might dominate, but as the temperature increases, chemisorption can take over. A practical example is dihydrogen adsorbing on nickel. Initially, hydrogen molecules are held by van der Waals forces, so physical adsorption. But then, the molecules dissociate into hydrogen atoms, which are bonded to the surface through chemisorption. This illustrates how the two types can work together depending on conditions. So, understanding these two adsorption mechanisms helps us grasp how gases interact with solids in various applications, from catalysis to filtration. Let's start by discussing the lack of specificity in physical adsorption. Essentially, a given surface of an adsorbent doesn't prefer one gas over another because van der Waals forces are universal. This means the attraction is fairly non-selective across different gases, which is an important point to remember. Next, the nature of the adsorbate itself plays a role. The amount of gas that a solid can adsorb depends heavily on the gas's properties. Generally, gases that are more easily liquefiable, meaning they have higher critical temperatures, are more readily adsorbed. This is because van der Waals forces are stronger near the critical temperatures, making adsorption more favorable. Moving on to the reversible nature of physical adsorption, this is quite significant. The process is generally reversible, meaning if you increase the pressure, more gas gets adsorbed because the gas volume decreases. Conversely, if you decrease the pressure, the gas can be desorbed easily. Since this process releases heat, it's exothermic, and it tends to occur more at lower temperatures. According to Le Chatelier's principle, increasing temperature reduces adsorption. Now, let's talk about the surface area of the adsorbent. The bigger the surface area, the more adsorption you get. That's why finely divided metals or porous materials with large surface areas are excellent adsorbents. They provide more surface for the gas molecules to stick onto. Finally, the enthalpy of adsorption is relatively low, typically between 20 and 40 kJ per mol. Although physical adsorption is exothermic, the weak van der Waals forces mean the attraction between the gas molecules and the surface isn't very strong. This low enthalpy is characteristic of physisorption and helps explain why the process is easily reversible. Let's discuss the key characteristics of chemisorption. First, it has high specificity, meaning it only occurs if there's a potential for chemical bonding between the adsorbent and the adsorbate. This specificity makes chemisorption quite selective. Next, it is generally irreversible because it involves the formation of a chemical compound, which doesn't easily break apart once formed. Chemisorption is also an exothermic process, releasing energy as bonds form. However, it's important to note that at low temperatures, this process tends to be slow due to the high energy of activation needed. As the temperature increases, the rate of chemisorption usually increases, similar to other chemical reactions. Another interesting point is that physisorption, which happens at low temperatures, can transform into chemisorption at higher temperatures. Plus, high pressure often favors chemisorption, making it more likely to occur under such conditions. Overall, these characteristics highlight how chemisorption is a specific, energy-dependent process that can be influenced by temperature and pressure, aligning with the broader theme of surface interactions and adsorption phenomena. Now let's look at surface area. Similar to physical adsorption, chemisorption also tends to increase as the surface area of the adsorbent expands. Essentially, the larger the surface, the more sites are available for the adsorbate to interact with, which boosts the overall adsorption capacity. Moving on to the enthalpy of adsorption, or the heat involved during the process. For chemisorption, this value is quite high, typically between 80 to 240 kilojoules per mole. This is because chemisorption involves the formation of chemical bonds, which requires more energy compared to physical adsorption. These points are crucial because they highlight how the nature of the surface and the energy involved dictate the effectiveness and mechanism of adsorption, tying directly into our broader discussion on how different adsorption processes operate and their applications. Now, let's look at how the amount of gas adsorbed by an adsorbent varies with pressure at a constant temperature. This relationship is typically represented by a curve known as an adsorption isotherm. One important example of this is the Freundlich adsorption isotherm. Freundlich introduced this in 1909, and it's an empirical relationship, meaning it's based on observed data rather than derived from first principles. It relates the quantity of gas adsorbed per unit mass of solid to the pressure at a specific temperature. This relationship is expressed mathematically by a particular equation, which helps us understand and predict how gases behave during adsorption processes. Recognizing these isotherms allows us to analyze and optimize adsorption systems, which is crucial in many industrial applications. So, in essence, adsorption isotherms like Freundlich's give us valuable insight into how gases interact with solid surfaces under different pressures, tying directly into our overall theme of understanding and controlling adsorption phenomena. Now, let's look at this relationship between the amount of gas adsorbed and the pressure. Here, X represents the mass of gas adsorbed per unit mass of the adsorbent. At a given pressure P, the constants K and N are crucial because they depend on the specific nature of both the adsorbent and the gas, as well as the temperature we're working with. This relationship is typically represented as a curve, where we plot the mass of gas adsorbed per gram of the adsorbent against pressure. These curves give us a clear visual of how adsorption behaves under different pressures. One key point to note is that at a fixed pressure, as temperature increases, the amount of physical adsorption actually decreases. This is because higher temperatures tend to reduce the tendency of gas molecules to stick to the surface. And you'll also see that these curves tend to approach a saturation point at high pressure, indicating that the adsorbent is becoming fully occupied. Understanding these curves helps us interpret how adsorption varies with pressure and temperature, which is essential for designing effective adsorption systems in various applications. Now, to verify the validity of the Freundlich isotherm, we plot log xm on the y-axis, which is our ordinate, and log p on the x-axis, the abscissa. If this plot results in a straight line, then the Freundlich isotherm holds true for the system we're studying. Conversely, if the data doesn't form a straight line, then the model isn't valid in this case. The slope of this straight line is particularly important because it gives us the value of 1n, which tells us about the intensity of adsorption. The intercept on the y-axis corresponds to log k, which relates to the adsorption capacity. It's also important to remember that the Freundlich isotherm describes adsorption behavior approximately. The factor 1, which appears as 1n, can vary between 0 and 1, indicating the range of the model's applicability. Because of this, the Freundlich equation is generally valid over a limited pressure range. When we take the logarithm of both sides of the original equation, it simplifies the analysis and makes it easier to interpret the experimental data in terms of linearity. Let's look at some specific cases in adsorption behavior. When 1 over n equals 0, it means that x over m remains constant regardless of pressure. In other words, the amount adsorbed doesn't change as pressure varies. This indicates that, under this condition, adsorption is independent of pressure altogether. Now, on the other hand, when 1 over n equals 1, it simplifies to x over m being directly proportional to pressure. So, in this scenario, the amount adsorbed varies directly with pressure, meaning if you increase the pressure, the adsorption increases proportionally. Both of these conditions are actually supported by experimental results, which is quite interesting. In practice, the isotherms tend to approach a saturation point at high pressures, meaning the adsorption levels off. This behavior at high pressure can't be explained by the Freundlich isotherm, though. The Freundlich model doesn't predict this saturation, which is why it fails to accurately describe adsorption at high pressures. This highlights the need for different models to better understand and predict adsorption behavior across the entire pressure range. Solids can adsorb solutes from solutions as well. For example, if you take a solution of acetic acid in acetic acid and shake it with charcoal, a part of the acid actually gets adsorbed by the charcoal. As a result, the concentration of the acid in the solution decreases. Now, when we look at adsorption from the solution phase, there are a few key observations to keep in mind. First, the extent of adsorption tends to decrease as the temperature increases. So, higher temperatures generally reduce how much solute the solid can adsorb. Second, the more surface area the adsorbent has, the greater its capacity to adsorb solutes. Think of it like having more seats or hooks for the molecules to stick to. More surface area means more adsorption. Third, the concentration of the solute in the solution also influences adsorption. Typically, a higher concentration of solute leads to more adsorption, since more molecules are available to interact with the adsorbent. Finally, the nature of both the adsorbent and the adsorbate plays a crucial role. Different materials interact differently, so their chemical nature affects how much solute they can adsorb. Understanding these points helps us grasp how adsorption works in real-world solutions, and it ties into the overall theme of how materials interact at surfaces and interfaces. Freundlich's equation provides an approximate way to describe how adsorption behaves from a solution. Instead of pressure, as in other models, it considers the concentration of the solution. So, it relates the amount adsorbed to the concentration in the solution at equilibrium, which we denote as C when adsorption is complete. C represents the equilibrium concentration. Now, if we take the logarithm of this equation, we get a linear relationship between log m and log c. This means that if we plot these two on a graph, we should see a straight line. The straight line indicates that the Freundlich isotherm is valid for the system we're studying. To test this experimentally, we can take solutions of different concentrations of acetic acid. We add equal volumes of these solutions to equal amounts of charcoal in different flasks. After allowing time for adsorption, we measure the final concentration in each flask. The difference between the initial and final concentrations tells us how much was adsorbed, which we call X using the equation we discussed. We can then verify whether the Freundlich isotherm applies by seeing if the data fits the straight line pattern. This approach helps us understand the adsorption process more thoroughly and confirms the model's validity in real-world scenarios. Now, let's explore some key applications of adsorption. First, the production of high vacuum. When we evacuate a vessel with a vacuum pump, there's always some residual air traces left. These traces can be adsorbed by charcoal, which helps us achieve a very high vacuum. This process is crucial in various scientific and industrial applications where a near-perfect vacuum is required. Next, we have gas masks. These devices are essential for safety, especially in coal mines, where poisonous gases can be a serious hazard. Gas masks typically contain activated charcoal or a mixture of adsorbents. The activated charcoal effectively adsorbs harmful gases, making it safe for miners to breathe in such dangerous environments. Finally, controlling humidity is another important application. Silica gel and aluminium gels are commonly used as adsorbents to remove moisture from the air. This helps in maintaining the right humidity levels, which is vital in preserving sensitive materials, pharmaceuticals, and even in everyday storage. So, as you can see, adsorption plays a significant role across different fields, from creating high vacuums to ensuring safety and maintaining proper environmental conditions. Now, let's look at some practical applications of adsorption. First, animal charcoal is commonly used to remove coloring matter from solutions. It works by adsorbing the colored impurities, effectively decolorizing liquids. Next, in the realm of industrial chemistry, heterogeneous catalysis involves the adsorption of reactants onto the surface of solid catalysts. This process increases the rate of reaction significantly, and many important gaseous reactions rely on solid catalysts to proceed efficiently. Moving on, adsorption also plays a key role in separating inert gases. Since different gases adsorb to charcoal to varying degrees, we can separate noble gases by exposing a mixture to coconut charcoal at different temperatures. This difference in adsorption helps us isolate specific gases effectively. In medicine, adsorption is used in curing diseases. Certain drugs work by adsorbing germs or toxins, helping eliminate them from the body more efficiently. Another fascinating application is the froth flotation process. Here, low-grade sulfide ore is concentrated by separating it from silica and other impurities. This is achieved using pine oil and frothing agents, which create bubbles that carry the sulfide particles to the surface for collection. Finally, adsorption indicators are used in titrations. Surfaces of precipitates like silver halides can adsorb dyes such as eosin or fluorescein. When this happens, they produce a characteristic color change, helping us identify the end point precisely. All these examples highlight how adsorption is a versatile and vital process across various fields, connecting fundamental principles to real-world applications. Now, let's talk about chromatographic analysis. This technique is fundamentally based on the phenomenon of adsorption, which involves the separation of components as they adhere to a surface. It's a powerful method because it allows us to analyze complex mixtures with high precision. You'll find that chromatography has a wide range of applications, both in the analytical lab setting, like identifying and quantifying substances, and in industrial processes, such as purification and quality control. Overall, chromatography exemplifies how understanding adsorption can be harnessed for practical and vital purposes across various fields. When we apply an electric potential across two platinum electrodes immersed in a colloidal solution, something interesting happens. The colloidal particles start to move toward one of the electrodes. This movement is called electrophoresis. Now, the key point here is that positively charged particles will move toward the cathode, which is the negatively charged electrode, and negatively charged particles will head toward the anode, the positively charged electrode. This movement of particles under an electric field is quite fundamental in many separation and analytical techniques. It's important to understand that electrophoresis relies on the charge of the particles and the electric field to drive their movement. Now, there's an interesting twist when we try to prevent this particle movement, say, by some means of immobilizing or stabilizing the particles. When we do that, and the particles are prevented from moving, the entire dispersion medium, or the liquid surrounding the particles, actually begins to move in response to the electric field. This phenomenon is known as electroosmosis. So, in summary, electrophoresis involves particle movement driven by electric fields, with the charge of the particles determining their direction. And when particle movement is hindered, the liquid itself moves, which is what we call electroosmosis. Both processes are key to understanding how colloidal systems behave in electric fields, and they play a significant role in various applications in chemistry and material science. Thank you so much for your attention today. I truly appreciate your time and engagement. I hope the insights shared have been helpful and inspire you to take action. Remember, the key points we've discussed reinforce the importance of continuous learning and adaptation in our field. Connecting these ideas to the overall theme reminds us that success comes from applying what we've learned and staying committed to growth. Once again, thank you for being part of this journey. I look forward to seeing how you implement these concepts moving forward.